Usually when we talk about a medical diagnosis, there's like this expectation of precision, right? It's kind of like engineering. You break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
Right, yeah. It's binary, broken or not broken.
Exactly. It's super clean.
Yeah.
But then you stepped into the world of enterprise storage and high availability architecture, and suddenly that x-ray machine is just, well, is broken. We're looking at a diagnostic landscape that is, honestly, incredibly murky.
Oh, totally.
Because when a multi-million-dollar cluster fails, finding the root cause requires understanding this massive invisible web of interconnected dependencies. You aren't just looking for a broken wire. You are looking for cascading logic failures.
It is the absolute definition of diagnostic muddy waters, truly. And frankly, that is exactly why enterprise certifications exist in the first place. They are designed to train you to navigate that immense complexity, before you are staring at a down system at 2 in the morning.
Yeah, nobody wants that. So welcome to this deep dive. Our mission today is conquering the core technical concepts and the assessment criteria of the NS0-094 exam.
Let's do it.
Just to ground you in the foundational info regarding this exam, this is a 90-minute proctored certification. It consists of 60 multiple-choice questions, which features both single and multiple response formats, and it's delivered in English.
But just to be clear, we aren't just going to read you an answer key today. That wouldn't help you much in the real world when the pressure is actually on.
No, not at all. This course focuses on giving you a step-by-step, question-by-question analysis of 10 actual practice questions. We are going to delve deeply into the problem-solving logic and the core knowledge points underlying each one of them.
Right, the real mechanics of it.
Exactly. So I'll read aloud the full text of every practice question, and together we are providing a detailed item-by-item breakdown of all options A, B, C, and D, accompanied by our audio commentary, specifically explaining why each option is correct or incorrect.
Because honestly, in a high-stakes environment, knowing exactly why a tempting answer is wrong is, well, it's just as critical as knowing why one is right.
Absolutely. So let's get into it. Before a storage system can do anything intelligent, its physical foundation has to be flawlessly constructed. We're going to start by looking at how hardware is connected and scaled. So here's the full text of question 2. When daisy-chaining multiple disk shelves in a single SAS stack, what dictates the maximum number of shelves supported?
Okay, classic scaling question.
Right, and the options are A, the physical length of the SAS cables provided in the original packaging. B, the total wattage capacity of the power distribution units in the rack. C, the specific hardware limitations of the storage controller and the shelf module types. D, the number of available Ethernet ports on the baseboard management controller.
So if you're looking at these options as an engineer trying to, scale up a rack, the temptation is definitely to look at power first.
Right, I instantly think of this like plugging too many extension cords into a single wall outlet.
Yeah, the daisy chain trap.
Exactly. At some point, you just don't have enough juice to spin up like 80 hard drives. So wouldn't power be the ultimate bottleneck, making option B the answer?
Well, it's a completely logical assumption, but in this specific context, power isn't the limiting factor for the data architecture itself. The correct answer is actually C, the specific hardware limitations of the storage controller and the shelf module types.
Okay, so you're saying the controller acts as the bottleneck because, well, every time you add a drive, you're asking the CPU to manage more address spaces, and eventually it just runs out of memory mapping.
You nailed it. Yeah. Think of the storage controller as an air traffic controller. It only has so much memory and processing bandwidth to keep track of individual drives. The hardware capabilities of the controller, combined with the chips inside the SAS modules, they define these strict limits on how many devices can be addressed, as well as, maintaining the signal integrity.
Right, that makes sense.
Yeah. And if we look at the other options, A is incorrect because cable length just dictates the physical distance between chassis and a rack. It has literally zero bearing on the logical device limit. B, the PDU wattage, that dictates how much power your physical rack can pull from the facility, but it doesn't limit the SAS protocol's logical limits.
Gotcha. And looking at D, the number of available Ethernet ports on the baseboard management controller, that feels like a total trap. The baseboard management controller, BMC, is just for out-of-band management, right? Like remotely powering the box on or off.
Exactly. It's a completely separate subsystem. The BMC sits on an entirely separate network. It has absolutely nothing to do with the high-speed SAS data path that actually talks to your hard drives.
Right. Okay, sticking with that physical foundation, what happens when we start wiring two controllers together for redundancy? Let's look at question 1. In a high availability controller configuration, what is the primary consequence of crossing the SAS cables between the local and partner storage stacks?
Oh, this is a dangerous one.
Yeah, the options are A. It creates an unsupported split fabric condition that prevents proper disk takeover during a controller failure. B. It causes the storage operating system to automatically convert the stacks into a single unified loop. C. It forces the baseboard management controller to initiate a thermal shutdown sequence. D. It triggers a hardware fault LED on the power supply units of the attached disk shelves.
The correct answer here is A. Crossing those cables creates an invalid wiring topology, which fundamentally breaks the expected ownership model of the disks.
Let me make sure I'm visualizing this correctly. In a high availability setup, controller 1 needs to know exactly which disks belong to it, right? And which belong to controller 2.
Yes.
That way, if controller 2, catches fire, controller 1 can instantly take over its disks. If you accidentally cross the SAS cables, you introduce ambiguity. The system essentially gets confused about who owns what, which makes a seamless failover impossible.
That is the exact mechanism. You are essentially creating a split-brain scenario on the back-end wiring.
Okay, but look at option B. Wouldn't a modern, highly intelligent storage system just realize the mistake and auto-convert those crossed cables into a single unified loop?
See, that's a great example of expecting software to fix a hardware layer 1 mistake.
No?
Enterprise storage systems are incredibly smart, yes, but they are also incredibly rigid by design to protect your data.
They don't improvise.
Exactly. They will not silently invent a new, unsupported architecture on the fly to cover up a cabling mistake. They will just halt and fail to prevent data corruption.
Which makes sense when data integrity is the goal. And if we look at C and D, those feel fundamentally disconnected from data paths entirely. Why would a data cable mix-up trigger a thermal shutdown or a power LED?
It wouldn't. Option C is wrong because thermal sensors are tied to the BMC's environmental monitoring matrix. They are strictly looking for, fan RPM drops or ambient heat spikes in the chassis. A logical SAS error won't change the physical temperature of the silicon. And D is incorrect because power supply LEDs only report electrical faults like a blown capacitor or a dead power feed. They do not care about data topology errors at all.
So if crossing cables causes that much chaos, how do you actually prove your pathways are clean before the system is even online? That real-world scenario is exactly what question 8 tests.
Yes, a very practical scenario.
It asks, after cabling a new SAS disk shelf, how does an engineer physically verify that multipath high availability has been correctly established without accessing the operating system? And the options are A. By observing the link status indicator LEDs on both input and output ports of the shelf modules. B. By listening for a specific diagnostic beep code emitted by the chassis speaker. C. By connecting a multimeter to the grounding terminal of the rack structure. D. By checking the thermal sensor readout on the primary power supply unit.
Yeah, this is a scenario every field engineer faces.
But let me push back on the premise for just a second. Why not just log into the operating system and run a diagnostic command? Why are we verifying this physically? It feels archaic.
It does feel a bit old school, I'll admit, but imagine you are racking equipment in a freezing, incredibly loud data center.
Fair point.
The cluster isn't fully initialized yet, or maybe the networking team hasn't even configured your IP addresses yet. You need a quick, immediate OS-independent way to validate that you haven't messed up the hardware redundancy before you leave the hot aisle. So the correct answer is A. You check the link status indicator LEDs on both the input and output ports of the shelf modules.
Because if the light is green, the path is clean. It's an instant visual confirmation at the hardware layer.
Exactly. When both physical paths are active, those LEDs glow. Let's dismantle the others. Option B, beep codes. This isn't a 1998 desktop computer failing a RAM check. Modern enterprise storage just doesn't rely on chassis speakers to confirm HA data paths.
Right. And C, a multimeter to the grounding terminal. I can sort of see why someone might guess that if they hear the word physical test, but a multimeter tests electrical safety and grounding, not logical data pathways.
Spot on. And D is incorrect for the exact same reason we discussed in the previous question. Thermal sensors measure heat, not SAS link redundancy.
All right, so our physical foundation is solid. The system is cabled correctly. Now we move to section 2. The system's identity and brains. How does it actually know who and what it is? This leads us to the internal boot media. Let's look at question 4.
Okay, let's hear it.
When replacing a faulty controller motherboard in an active-active pair, why is it critical to physically transfer the original boot media to the new motherboard? And the options are A, to preserve the physical hardware warranty registration details. B, to ensure the replacement controller boots with the correct system configuration and system identity. C, to maintain the active network link states on the cluster interconnect switches. D, to prevent the NVRAM battery from discharging during the replacement procedure.
Interesting one.
So let me play devil's advocate here. If I'm putting a brand new motherboard into the chassis, wouldn't it be much safer to just start fresh? Like boot it up blank and let it re-download all its settings from the network, kind of like syncing a new smartphone from the cloud.
I see the logic there, I really do, but enterprise storage clusters are incredibly paranoid about rogue nodes trying to join their network.
Paranoid.
Highly paranoid. They operate on strict quorum rules. The boot media contains the node's unique software identity, its local configuration, and its cryptographic cluster membership details. If you boot a new motherboard without that original boot media, the cluster sees a completely unknown alien node and aggressively rejects it.
Oh, okay.
That's why B is the correct answer. You have to transfer the drive to ensure the new hardware assumes the exact identity of the old hardware.
It's basically a brain transplant. That eliminates option A pretty cleanly, right? Hardware warranties are usually tied to the physical chassis serial number, or like M address burned into the metal. They aren't stored on a removable flash drive.
Correct. And option C is incorrect because physical network link states, meaning the green lights on your switch, they operate at physical layer 1. They have absolutely nothing to do with what boot drive is plugged into the motherboard.
And D, preventing the NVRAM battery from discharging. I mean, the NVRAM battery is a totally separate component. Moving a flash drive doesn't alter battery chemistry.
Precisely. They are completely unrelated physical systems.
Which perfectly sets up the stakes for question 7. If the primary internal boot media experiences a catastrophic hardware failure, what is the immediate physical indicator on the controller?
Oof, catastrophic failure.
Yeah. The options are A, all drive LEDs on the attached shelves will flash synchronously. B, the baseboard management controller will permanently lock the console port. C, the controller will fail to load the operating system and halt at the firmware level. D, the system will automatically eject the faulty boot device from its slot.
Let's hear your thoughts on this one.
Well, I immediately want to throw out option D. I mean, hint a funny picture, but enterprise controllers don't have spring-loaded mechanical ejection mechanisms because moving parts introduce physical points of failure. It's not like a VCR that's going to spit a broken USB drive across the room.
You're exactly right. They are built solid, no unnecessary moving parts. The correct answer is C. The controller simply fails to load the OS and halts at the firmware or bootloader level. What's really fascinating here is how the system protects itself when it loses its quote-unquote brain. It essentially freezes in a safe state because without an OS, it simply doesn't know how to safely write data.
It just stops. So what about option A, the drive LEDs flashing?
Option A is incorrect because the drive LEDs on the external shelves indicate user data activity. The external drives have no idea what's happening with the internal boot state of the controller.
Makes sense.
And option B is wrong because the BMC would actually keep the console port open. You desperately need that console port to troubleshoot the halted system. Locking it out would be completely counterproductive.
Okay, so the system is booted, it has its brain, it knows its identity. Let's move to section 3. As the system starts taking in data like the write requests from users, it needs a totally secure place to hold those thoughts before committing them to long-term storage. Enter NVRAM. Let's look at question 5.
The short-term memory.
Right. What is the primary hardware function of the non-volatile random access memory within the storage controller architecture? Here are the options. A, to permanently archive old performance data for compliance auditing. B, to store the master copy of the system firmware for emergency recovery. C, to buffer incoming network traffic before it reaches the host bus adapters. D, to safely cache incoming write requests until they are committed to persistent physical media.
NVRAM is such a critical component.
So, if I understand the architecture right, NVRAM is basically like hitting quick save in a video game right before a boss fight. It's a fast, perfectly safe way to ensure you don't lose your exact progress if the power goes out.
That is a brilliant analogy. Yes, option D is the correct answer. The controller receives a write request from a database, immediately saves it into the super fast NVRAM, and tells the database, okay, I've got it. This provides incredible performance.
Well,
But because it's non-volatile, meaning it's backed by a dedicated battery or a supercapacitor instead of just standard volatile RAM, even if someone accidentally unplugs the entire rack right then, That data is perfectly preserved in the cache until power returns, and it can be permanently written to the hard drives.
That makes perfect sense. Let's look at the wrong answers. I can guess why A is wrong. NVRAM is expensive, highly limited real estate on the motherboard. You wouldn't waste it on permanently archiving gigabytes of old performance data. You just dump that to cheap disk storage.
Spot on. Option B is incorrect because, as we just learned in the last section, the system firmware lives on the boot media, not the NVRAM cache.
Right. And C, buffering network traffic.
Network buffering happens dynamically in the standard RAM located on the host bus adapters or network cards themselves. NVRAM is strictly reserved for protecting uncommitted incoming data writes.
Which brings us to a massive real-world risk in question 6. When preparing to replace a failing NVRAM battery, what must be confirmed before physically removing the controller module from the chassis? The options. A. The partner node has successfully powered off to prevent split brain syndrome. B. The system has gracefully halted and all cached data has been destaged to the storage media. C. The cluster interconnect links have been manually disabled using the baseboard controller. D. The replacement battery has been pre-charged to at least 80% capacity.
This is a scenario where you really don't want to mess up.
Yeah, based on what we just discussed, if that battery is keeping unwritten data alive, pulling the controller out while it's active would be catastrophic. So the answer has to be B, right? The system must be gracefully halted, ensuring all that cached data in the NVRAM is destaged, meaning permanently flushed out to the physical hard drives.
If you get this wrong, in the real world, you permanently destroy client data. Yes, B is correct. Because if you just yank the controller out while the battery is dying, anything floating in that NVRAM quick save state just vanishes forever the second the physical connection breaks.
Brutal. So why are the other options such bad ideas? Option A says power off the partner node.
Powering off the partner node would actually cause a massive self-inflicted outage. You want the partner alive so it can take over operations while you service the broken controller.
Oh, of course.
And option C is incorrect because disabling cluster links just isolates the node from the network. It does absolutely nothing to protect the data trapped in the local memory.
And D, pre-charging the replacement battery. I mean, sure, good practice to have a working battery, but pre-charging the new one does absolutely nothing to protect the data that is currently sitting at risk in the old hardware. The priority is destaging the data first.
Exactly. You secure the data, then you worry about the hardware.
Okay, we've secured the local controller and its memory. To finish our deep dive in Section 4, we are looking outward at the nervous system. How does this controller safely connect to a larger cluster and expand its capabilities? Let's analyze question 3.
Let's do it.
What is the strictly enforced hardware requirement for deploying a multi-node cluster interconnect fabric? Options. A. Using dedicated vendor-validated switches that are completely isolated from the customer data network. B. Ensuring all nodes are connected using direct attached copper cables without any intermediary devices. C. Deploying identical optical transceivers across both the management and cluster network ports. D. Routing the cluster traffic through the primary core router to ensure centralized monitoring.
Any immediate thoughts?
Yeah, it can instantly eliminate D. Routing cluster traffic, which needs to be lightning fast, through a primary core router is a recipe for disaster. A router introduces multiple hops, complex routing tables, and huge latency. You want cluster nodes talking directly, right?
Completely correct. Cluster interconnects must be flat, layer 2 networks. To guarantee the high availability, you must use dedicated vendor-validated switches that are physically or logically isolated from regular customer traffic. So A is the correct answer.
Because if someone decides to, say, download a massive file on the main corporate network, you don't want that congestion choking the storage nodes when they are trying to synchronize a critical failover.
Exactly. Let's look at why B is wrong. Direct attached copper cables without switches only work for a 2-node switchless cluster. If you have a multi-node cluster, meaning 3 or more controllers, you fundamentally need intermediary switches to route the traffic between them all.
Makes sense.
And option C is incorrect because management ports usually run at slower legacy speeds like 1 gigabit, while custom ports run at 40 or 100 gigabit. They physically cannot use identical transceivers.
Speaking of transceivers, let's hit question 9. What is the consequence of utilizing an unsupported third-party optical transceiver in a high-speed cluster interconnects port? Options. A. The system will automatically rewrite the transceiver firmware to match the vendor standards. B. The port will default to half-duplex mode to prevent data corruption. C. The hardware may physically disable the port or generate continuous uncorrectable transmission errors. D. The transceiver will permanently lock itself to the internal routing table.
I love this question.
And I want to pause and address a common complaint here. Are vendor-validated parts really necessary, or is this just an artificial way for companies to force you to buy their specific brand of expensive cables?
I totally understand the skepticism, and it's a debate in every IT department, but you really have to respect the physics here.
The physics.
Yeah, at cluster speeds, we're talking tens or hundreds of gigabits per second. The physical tolerances for electrical signals and light wavelengths are microscopic. If a cheap third-party transceiver drifts out of spec by a fraction of a nanosecond, it corrupts the data frames on the wire. Therefore, C is the correct answer. The system's hardware is designed to protect the integrity of the cluster. It will either physically disable the port at the hardware level, or it will throw continuous uncorrectable transmission errors because it literally cannot cleanly read the distorted light signals.
Wow, okay. That makes total sense when you frame it around physics rather than just corporate greed. And honestly, I'd throw out option A immediately.
Right.
The idea that a storage controller is going to magically reach into a physical third-party transceiver and expertly rewrite its hard-coded proprietary firmware just sounds like science fiction.
It is. A storage controller is not a universal firmware flasher. Let's look at B-half duplex mode. That is a legacy concept from early 2000s Ethernet hubs. Modern high-speed fiber optics do not fall back to half duplex to save themselves. They either link at full duplex or they fail.
Right. And D is incorrect because transceivers are dumb. Layer 1 physical devices. They just turn electricity into light. They do not possess the logic to lock themselves to software constructs like Layer 3 routing tables. All right, our final piece of the puzzle. Adding expansion cards. Question 10. When installing a new PCIe host bus adapter into an existing controller, why is it necessary to respect the specific slot assignment rules defined by the vendor? Here are the final options. A, to ensure the front bezel can close securely over the chassis. B, to guarantee optimal bus bandwidth allocation and prevent hardware recourse conflicts. C, to maintain physical alignment with the external cable management arm. D, to synchronize the LED blinking patterns with the primary motherboard indicators. Let's break these down. Well, looking at these options, A, C, and D feel like purely physical or cosmetic distractions. The front bezel, option A, goes on the front of the chassis while PCIe cards are installed in the back. Maintaining alignment with the cable arm, option C, is just external tidiness. And synchronizing blinking LEDs, option D. That's just for show. So it has to be B, guaranteeing bandwidth allocation. But what does that actually mean under the hood?
Under the hood, not all PCI slots are created equal. Inside the controller, some slots have 16 lanes wired directly into the CPU for maximum throughput. Other slots might only have 4 or 8 lanes, and they might route through a chipset bottleneck.
Ah, I see.
The vendor maps out specific slot assignment rules so that a massively demanding 100 gigabit networking card actually gets plugged into a direct CPU path, guaranteeing the bandwidth it needs, while a slower legacy SAS adapter gets put in a slower slot to prevent them from fighting over the same internal resources.
Oh, it's basically about making sure your sports cars get the fast lane and your delivery trucks stay in the slow lane.
Exactly. Option B is the correct answer because respecting those slot rules prevents those internal traffic jams.
Thanks for joining us on this deep dive.